Have you ever wished for a way to measure a tiny electrical signal without disturbing it at all? Or to connect two parts of a circuit together without one affecting the other in an undesirable way? Imagine a perfect interface component that just listens without ever drawing power from the source. The concept of an ideal operational amplifier, or op-amp, having infinite input impedance means it gives us precisely that capability. It acts like a perfect, non-intrusive sensor that draws absolutely no current from the signal source it is monitoring. This characteristic is fundamental to its versatile behavior. This seemingly straightforward characteristic of zero input current is profoundly significant. Consider this. If no current flows into the input terminals of an ideal op-amp, then there can be no voltage drop across any internal resistance within the signal source itself. This completely eliminates what engineers refer to as loading effects. In practical electronics, when one circuit component loads another, it draws current, which can cause the signal voltage to decrease or its waveform to distort. The infinite input impedance of an ideal op-amp ensures that the integrity of the signal is perfectly preserved as it enters the amplifier. It essentially creates an electrical wall, perfectly isolating the input from the internal workings of the amplifier circuit, which is why op-amps are exceptional voltage buffers. This allows for consistent and predictable performance regardless of the source's characteristics. Engineers powerfully leverage this ideal property in countless crucial applications. For example, when working with transducers or sensors that inherently possess a very high output impedance, like certain pH probes or piezoelectric sensors, directly connecting them to a typical amplifier can severely attenuate their tiny output voltage. An op-amp with its effectively infinite input impedance can measure the sensor's voltage without diminishing it in the slightest. This enables accurate, stable readings from sources that would otherwise be too fragile or weak. This characteristic is also indispensable for creating active filters that precisely shape frequencies without signal loss, designing precision voltage followers for impedance matching, and implementing instrumentation amplifiers, where differential input signals must be processed with extreme accuracy and minimal current draw. This ideal characteristic of infinite input impedance underpins one of the fundamental, golden rules for simplifying op-amp circuit analysis. The current into both input terminals is zero. This principle, alongside the virtual short concept for negative feedback configurations, forms the cornerstone for quickly deriving the voltage gain equations for nearly all common op-amp circuits, including inverting, non-inverting, and differential amplifiers. While real-world op-amps do not have truly infinite input impedance, modern devices often achieve values in the gigaohms or even teraohms range, especially those employing field effect transistors in their input stages. This near-ideal behavior allows engineers to design complex analog systems with confidence, knowing that the ideal model provides a highly accurate prediction of actual circuit performance. It is a powerful conceptual simplification that makes understanding and designing with op-amps for more accessible. Understanding the profound significance of infinite op-amp input impedance is absolutely vital for grasping how these incredibly versatile devices can provide almost perfect signal isolation and precise amplification without ever degrading the source signal. This characteristic not only drastically simplifies the theoretical analysis of complex circuits, but also empowers engineers to design robust, predictable, and highly accurate analog systems that can faithfully process even the most delicate electrical signals. It is a foundational concept that enables the creation of high-performance precision electronics across numerous industries, making previously impossible measurement and signal conditioning tasks a reality.